We begin our study of statistics by taking a look at an introduction to statistics. If your experience has been having taken a statistics course before and you didn't like it or didn't understand it, don't be afraid. It's actually quite a useful subject and something that we're going to spend a fair amount of time with in this course, and hopefully show the practical application of statistics. You know, there's a good reason why we use statistics, as mentioned in an earlier course. Statistics helps us manage risk. When we can't know the entire population of a data set, which is very, very commonly the case, we use samples and other statistics to help us understand or gain some insight into what that population might look like, and then hopefully in ways that it might behave into the future. So by way of definition, mathematics deals with sort of pure, although at times somewhat abstract thought, but it generally results in a singular answer. So this is what we call deterministic mathematics. 1 plus 1 is 2, at least in base 10. Statistics, though, deals with some component of an unknown. So it's incomplete data, but what we're trying to do is use that incomplete data to make some kind of an inference about a larger data set. And that's why we call it probabilistic. You know, with some level of probability, we believe we can gain insight into a population and describe it with a certain level of sort of accuracy. Now, one thing we're going to learn about samples versus population is all samples have error, and as you can see here, if what's represented here by the colored dots in the center, if that's our population and we're drawing various samples from that, we can see that each sample will look just slightly different from the population. Some will represent it very well and some won't represent it well at all. And so just recognize that all samples have error, and this can be problematic when you're talking to somebody who doesn't fully understand or appreciate what we're trying to do with inferential statistics. So just be mindful that some of the pushback you'll get sometimes is, well, if samples have errors, then why are we bothering? Why not look at the population? Well, that might not be practically feasible. In many cases, it's not. But I would also say that even by looking at the entire population, we can never be sure we've got a fair assessment as to what we're looking at, because what it assumes, or what that assumes, is that people don't make mistakes, and of course we all do. So by looking at all of the data points in a data set, or all of the items in a population, doesn't assure us of 100% accuracy. It just maybe gives us the perception that we have it, but certainly we all make mistakes, and that can happen whenever we're looking at an entire data set. So taking samples is a valid approach, and as you'll see as we go through that's part of the Lean Six Sigma training, that it can be verified that the sample is a good representation of the population when we're careful and methodical about what we're doing and how we're going about it. We can do things with inferential statistics like making, again, an inference about a population. So we look at a sample, we make some assessments to what that sample looks like, and then we make an inference about the larger population. But ultimately what we're trying to do is something like this first example. We want to perhaps assess the mean of the population, and maybe in this case it's, we can say that the mean of the population is somewhere between 20 and 30 units, whatever that is, at the 95% confidence level. So, at the 95% confidence level, the population mean is likely to be between 20 and 30, inches or units, or whatever the unit of measure here is. Moving on, one of the best tools that you have available to you is just a basic statistics tool. So look at a data set and then run a bunch of preliminary sort of statistics on it. A couple of the first things you're going to do is check for the normality of the data. So that's something you always want to try and assure yourself. Maybe even before that, I want to back up here by saying plot the data and have a look at the distribution itself. And so having a view of that will tell you a lot about what it is you're facing in terms of the skew of the data, or maybe the kurtosis of the data. two other components that we use to assess normality. But then moving on to normality, we want to test whether or not it fits the normal model or the normal distribution model. And of course, other things like just understanding how many data points you're dealing with, the mean or what we call the simple average, the standard deviation and the variance. These are measures of dispersion. How much is the data dispersed away from the mean? And then also, what's the minimum value, what's the maximum value, and then how does it break up in terms of its quartiles? You know, if we break it up into sort of 4 equal parts, how does that lie? Things like the bin size, we don't get into too much, but determining bin size or bin width is a science in and of itself. And so, but for now, there are defaults in both Minitab, and I've put a default here in the basic statistics Excel spreadsheet as well. You can go ahead and look at those calculations if you want, but it is a science in and of itself. And then, of course, perhaps we want to assign some confidence level to our assessment of what we think the confidence interval will be around the mean. So remember, this is a sample, and we're trying to assess where we think the population mean lies, for example, but we don't know for certain, but we can determine a range with pretty good certainty. So we have confidence interval on the mean, on the median, on the standard deviation, and so forth. So I would say for any data set that you come across, run this set of statistics, and I think you'll find it's very sort of insightful as to what the data looks like and perhaps what you're what you're facing. Now, this notion of spread, how spread is your data? How much does it vary? There are two measures. Of course, the range is simply the maximum value in the data set minus the minimum value, so it's the width, if you like. But it's not very useful, and it is influenced by outliers. So we have a better measure. It's actually called the standard deviation, and the standard deviation is nothing more than a measure of the dispersion of the data. It is the average distance from the mean of all the data points, both to the left and to the right of the mean itself. Okay, so standard deviation is the average distance of all the other data points relative to the mean, both left and right. So that's standard deviation. So for people that are new to the concept, it can be difficult to understand, but it's one of the most important things, I believe anyway, that you'll come across in statistics. You're going to see standard deviation come up all the time. It's fairly ubiquitous in that it shows up just about everywhere, and it's a very, very, very useful tool. The normal distribution is a unique concept because many of the processes that you'll come across in your organization, certainly many in nature, follow a normal distribution. A normal distribution is nothing more than it's symmetrical around the mean. So if I look at a data set, I calculate the mean, then the data points on the left of the mean and the data points on the right of the mean, and the way they're distributed and the way they lie is reasonably symmetrical. And interestingly enough, we can completely describe a normal distribution with two things and only two things, at least that vary. One is the mean and the other is the standard deviation. And if I have those, then I can construct a normal or bell curve from that data set. And this is a really important concept that you're also going to see come up again and again. And then finally, how does this sort of tie together in the context of processes and process capability is where we're leading towards, at least one of the places we're leading towards. So if I have the bell curve represented here by the blue bell, so that's my data, that's the distribution of my data. I can certainly from any given data set calculate the standard deviation. And then I've got specification limits, LSL, lower spec limit, or USL, the upper spec limit. Those are given by customers or regulatory agencies or things of this nature, but they're not generally determined by the organization, unless, of course, it comes from engineering, but it's usually a customer-driven or regulatory-driven requirement. And what I'm trying to determine here is, given my process and the distribution of my data, how many standard deviations fit between the mean, which occurs right here in the center, and the spec limit. In this case, I've shown the upper spec limit, but the same is true towards the lower spec limit as well. And if I can fit 3 standard deviations between the spec limit and the mean, then I've got a 3 sigma process. Notice that as I have less distribution in my data, as I have less variation in my data, I can actually, my standard deviation, right, the degree to which my data varies is smaller, and so my standard deviation is smaller. Therefore, I can fit more of them between my mean and my spec limit. And so now I'm showing a 6 sigma process. Why? Because I can fit 6 standard deviations between the mean and a spec limit. And then finally, if I had something like a 9 sigma process, again, my standard deviation is now quite small, and I can fit more of them between my mean and my spec limit. And you'll notice in each case that I'm going to have fewer and fewer defects, that is, process output that exceeds one of the spec limits. So those occurrences may very well happen, but they will happen with far less frequency in a 9 sigma process than they would with a 6 sigma process than they would with a 3 sigma process. And I just happen to use those 3 numbers. I mean, really any number applies here. But that is the concept of a process that meets a customer's requirements given by the spec limits and the capability of that process. So I'm comparing the voice of the process, so that is the mean and standard deviation, versus the voice of the customer, which is the width of the spec limits.